Ever looked at a donut and, wondered if there's more to it than meets the eye? Well, today we're going on a journey, a deep dive, into the fascinating world of these shapes. Mathematicians, they call them tori. And what's really mind-blowing is that tori that seem totally different, like geometrically, can actually be considered the same, like fundamentally from a mathematical point of view.
It's like finding out that two things that look completely different are actually built from the same blueprint, right?
Exactly. And this hidden connection, it's called conformal equivalence. It's our key to unlocking some pretty surprising relationships in math.
And that's what makes this so cool. You know, we all have this picture in our head of a torus, that classic donut shape.
Yeah.
But math, it lets us be way more creative. We can build these surfaces in all sorts of abstract ways.
Right.
And then, boom, these different constructions. They might look nothing alike in the usual geometric sense, but they end up sharing this common complex structure.
Okay, so complex structure, that's a big one.
Yeah, it's the heart of conformal equivalence. It's saying these surfaces are, in a very real mathematical way, the same.
I love it. So to guide us on this adventure, we're going deep into this paper, Hopf tori and standard tori. And what got me excited about this paper specifically is how it tackles these really deep ideas using tools that are, relatively accessible. We're talking differential geometry.
Right. It's like a backdoor entrance to these concepts that are often explored with much more advanced math.
So what's our mission for this deep dive?
Our mission is to map out the conformal relationships between three main players. The standard torus, that's our classic donut friend. Then we have something called the product torus, which is a more abstract mathematical creation.
Okay, so the product torus, we're going to have to break that down.
Definitely. And last but not least, we have this enigmatic object called the Hopf torus. That's the wild one.
Okay, the Hopf torus. Sounds mysterious. I'm intrigued.
And the big reveal is going to be how these seemingly unrelated mathematical entities are actually deeply, deeply intertwined.
So why should all of this matter to, anyone listening?
Great question. I mean, yeah, there's the pure mathematical curiosity, which is huge, right? But it goes way beyond that. The ideas we'll be talking about, they have implications in all sorts of fields, like think Riemann surface theory. It's all about the geometry of surfaces in the complex plane, and it relies heavily on understanding these tori classifications.
Okay, so Riemann surface theory, check. What else?
Well, there's also a direct link to complex analysis. That's the study of functions of complex numbers. But here's the real kicker. These concepts even have connections to theoretical physics, especially areas like string theory.
Whoa, string theory. We're going big.
And get this, they also connect to the study of surfaces embedded in 3D space, like Willmore surfaces, which are all about minimizing this kind of bending energy.
Okay, so from donuts to string theory to bending energy, it's all connected. All right, let's start unpacking this. First up, the standard torus. It's usually denoted as TR/3. So picture this. You have a circle, radius 3, we'll call that the small circle, and you rotate it around a line. But this line, it's not going through the center of the circle. It's a distance $3, Trinity being bigger than tor, obviously.
Exactly, like spinning a hula hoop around your body, not through your hand.
And that spinning, that creates our donut shape. Now, because this torus exists in our normal 3D space, which has like a natural way to measure distances, the Euclidean metric, the surface of the torus, it also inherits this way to measure distances.
It's called the induced Riemannian metric.
Induced Riemannian metric. Okay, gotta love those math terms.
Think of it like this. Imagine a little ant, right? It lives on the surface of this donut. The induced metric is how that ant measures distances along that curved surface.
I love that, the ant's perspective. So the paper, it gives us a formula, right, for this induced metric.
Yeah, it's in terms of these coordinates, theta and phi. Think of a theta as the angle that tells you how far you've gone around the whole of the donut, the long way. And theta is the angle telling you where you are as you go around the smaller circle, like the cross section.
Got it. So like longitude and latitude on a donut.
Pretty much. And the formula for this metric, we call it $, is $, r plus r cos theta 2 plus r2 d theta 2.
Okay, now let's break that down. We see no cos and 32. What are those exactly?
So those terms, they represent teeny tiny changes, infinitesimal changes in our angles, theta and 30 teller. Theta Livy is like the smallest imaginable change in theta. And theta 2 to 2 is related to the square of that super tiny change. Same idea for theta 2 out 2.
Okay, so infinitesimal changes. Got it.
Now, the coefficients in front, the 32 and 22s and 22, those are the real players. They tell us how these tiny changes in our angles actually translate into distances on the surface.
So like a conversion factor.
Exactly. For example, if you take a tiny step, yeah theta, in the theta direction while keeping fin the same. The square of the actual distance you traveled is $ plus arco2 times giga2.
And that coefficient, it depends on there, right?
Right, which makes sense, because the distance around the donut hole, it's bigger on the outside than on the inside.
Of course, the outer circle is bigger.
When sins is $1 or $2, that's the outside, finis is 1, and the radius of that circle is $ plus area. But when fin, this is the inside, the theta sees is $1, and the radius is ln d. So confinpins is basically the radius of the circle you're moving on as you change the theta at a fixed $.
Okay, that makes sense. So what about the second term, the 2D fidelity?
That's all about the small circle, the cross-section.
Yeah.
If you move a little t-fin in the theta direction, keeping infin fixed, you're tracing out a small arc on that cross-section circle, which has radius $.
Makes sense.
And the square of that little arc's length. It's just 2 times ton, times 2 fill, just like we'd expect for a circle with radius $.
Perfect. So our metric plus, it's combining these two ways of moving on the torus, giving us the infinitesimal distance squared. Okay, next up. The paper introduces this almost complex structure denoted by J jollers, and it says it's compatible with our metric jollers and the orientation of the torus.
Okay, so almost complex structure. It sounds pretty abstract.
It does, yeah. What's the intuition here?
Think of it as a rule, a consistent way to define a 90-degree counterclockwise rotation at every single point on our surface.
A rotation, like on the surface itself?
Yep, on the torus. On a flat plane, that's easy, right? Just spin it. But on a curved surface, like our donut, it gets trickier.
Okay, so this rule, this J-joller, it's got to play nice with the curvature.
Exactly. It has to be compatible with the metric, meaning if you take two little tangent vectors at a point, those arrows showing directions, and you rotate one by 90 degrees using J-joller, the lengths and the angle between them, they have to behave nicely according to Dow.
Okay, and the orientation part?
That means it respects the inside and outside of the surface. Essentially, JB gives the torus a structure that, locally, looks like the complex plane. Remember, in the complex plane, we have multiplication by $, which is like that 90-degree rotation.
I'm starting to see the connection. So the paper then gives us how JB acts on these things called coordinate vector fields, partial theta and partial phi. Partial theta, that's the direction of change as we move along daily, keeping Hibia constant. Look, always moving along those longitude lines.
Right, and partial phi, that's the direction of change as we move along theta, keeping theta constant. Think those latitude circles.
And the paper gives us these equations, JB partial theta, far phi's, aphiolophyte, and hyperphi partial feet, and JB far phi and I phi. Can we unpack those?
Sure. These equations, they're telling us what happens when we take those basic directions on the torus, partial theta and partial phi, and we hit them with our 90-degree rotation, JBBB.
Okay, so we rotate those directions. What happens?
Look at the first one, J partial theta plus os Jacob partial theta. This says that if you're moving in the tighter direction along partial theta and you apply J to partial phi, you end up moving in the partial theta direction.
So a rotation. But there's more, right?
Yeah, your speed in that partial theta, it's scaled by this factor, partial phi plus r partial theta.
Okay, so it's not a simple rotation. There's a scaling factor. And the second equation?
The second one, J to particle theta plus r cothal theta, it's similar. If you're moving along particle theta and you apply JK to direct, you end up moving in the opposite theta direction along partial theta.
Opposite direction check.
And again, there's a scaling factor. This time it's far phi plus r cos phi.
So those scaling factors, they depend on phi. What's the significance of that?
The fact they're not constant, that they change with theta phi, it's a sign. It tells us that our original coordinate system, the theta and phi, even though they're good for describing the geometry, they're not perfectly aligned with this complex structure idea.
So they're not truly complex coordinates.
Right. In a perfect complex or analytic coordinate system, that rotation, that JB action, it would be much simpler. It would look like multiplication by weak taller in the complex numbers. Remember, if CLR is a complex coordinate, like ZOE plus IE, then multiplying by 2R rotates by 90 degrees. One per Shaluth and per Shaluth, one per Shaluth is more messy, which means CDAL and data aren't directly giving us that clean, complex behavior.
Okay, I see the issue. So we need new coordinates.
Yep, we need a coordinate system that plays nicer with the complex structure.
And that's where these special vector fields come in, right? The paper introduces $6 partial theta and datalers cola plus rx less lie fossil phi and Jago crucial. Why?
They're crucial because they satisfy these three important properties. 6y dollars y dollars, mevcut sayır, and ggx equals y to dollars y.
Okay, let's break those down. First one, $6 y dollars equals dollars y. That involves the lie bracket, right?
Yes, the lie bracket.
Not the friendliest concept. Can we make it intuitive?
Definitely. Imagine you're standing on the surface of our torus. Now imagine you can move in the direction of $6 for a tiny bit, then in the direction of dollars for a tiny bit. That's one path. Now do it in the opposite order. Move along dollar first, then 6.
Okay, so two slightly different paths.
If the lie bracket $6 is 0, it means those two paths, they end up at the same spot, at least to first order in those tiny movements. It means 6 dollars are commuting vector fields. Their flows play nicely together.
Okay, so the order doesn't matter. They commute. What about those other two properties? JGX was y minus SXC or DGX was $XX. Those look a lot like complex numbers.
Bingo. That's the big connection. You're mimicking how $1 works in the complex world. If we think of $6 as our real direction, then applying JGXI, or 90-degree rotation, gives us $1, which is like our imaginary direction.
I see it, yeah. JGXEX at $1, like multiplying 1 by orders to get $1.
And if we hit dollars with JDO again, we get JGYXAX6, which is like multiplying otter by I to get $2.
Mind blown. So 6 and dollars are giving us this complex structure locally.
Yes, they're forming a natural basis for it.
And this is where Frobenius's theorem comes in, right?
That's right.
It's a big theorem, but how does it help us here?
Frobenius's theorem, in our case, basically guarantees that because our vector field 6 to dollar commute, that lie bracket is 0, we can find local coordinates, let's call them VV, where partial U, the direction of change along 2, is exactly our 6 dealers, and partial V, the direction of change along theta, is exactly our dollars.
So Frobenius tells us these coordinates exist.
Yep. And having those coordinates is a huge step towards finding that complex structure, because now we're talking the same language as the complex plane.
And once we have those dollar coordinates, the paper shows that our jitter dollars, it acts like partial VO and jitter partial U.
Right, which is exactly how multiplying by dollar works on a complex coordinate. 0 will U plus IVO. It's beautiful how it all lines up.
It is. It's like we zoomed in and found a spot where the torus looks just like the complex plane.
Exactly. That's what we mean by local complex structure.
Okay, so how do we actually find these magic GOV coordinates?
That's where things get a bit more technical.
Hit us with it.
The paper introduces this function. It's an integral. Fe, thero phi phi caro plus r cos c. And it points out that because $3 is bigger than trailers, which are both positive, the derivative of $5, that's phi phi r plus r cos phi, it's always positive.
Okay, why is that positive derivative so important?
Because it means $5 is strictly increasing. It always goes up.
Yeah.
And that means it has an inverse function. We'll call that f-splitter. And this inverse, it's key to transforming our fiddle coordinate into the imaginary part of our complex coordinate. It's like we're stretching and warping theta in just the right way.
This function, $5, it's doing a lot of heavy lifting. The paper then looks at what happens when we move along the flow of this vector field, flas flightar plus Harcos 40. It's saying if you start at a point with coordinates and you follow this flow for some time, your theta stays the same, but your failure changes to some new value. Let's call it PS2.
And this psi, it satisfies this differential equation.
Yeah.
Fractured r co with the starting point factor co.
Okay, that's how phi evolves as we flow along.
Right. And the paper then shows that if you look at factar, its derivative with respect to fractar is just 1. That's a clever trick.
Okay, how does that work? Can we go through that step by step?
Absolutely. So we want the derivative of fret plus respect to the sire. We use the chain rule. Remember, factar is just a fractar plus r cos. So when we plug those in, we get fractar plus r cos and pi sire plus r cos. And then magic happens.
Pretty much. The prac plus r terms, they cancel out. And the dollars too. We're left with just 1.
Wow, that's elegant. So the derivative of fort t is 1. What does that tell us about 5 itself? It means 4 must look like te plus some constant, let's call it $6. To find $6, we use our starting point. Plugging in t, we get for dsa plus ca, so f phia. Therefore, we have phia t plus ea. To get phia, we need to use the inverse of f1t plus f phia. This tells us exactly how phia changes as we move along that flow of dollars.
It's all about finding the right transformations. Now, the paper defines this map, theta f of f1. It's saying that theta plus this is giving us those analytic coordinates we've been looking for. To see this, we look at the partial derivatives of phi. First, with respect to theta of phi. Since phi only depends on theta in its first component, the derivative is $1, which is just our $6, right?
That part's straightforward.
Now, the derivative with respect to this one looks a bit more involved.
So remember how Celas is connected to Celas through Fy, then Celas F1, then AF1, and the inverse function theorem tells us that FRAV1 is a FAVN, and we know FAFR is FRAF-RF. Putting it all together, we get Frosch by War Phi equal porous Phi, which is just FRAF4 partial Phi, which is our dollars.
So in these new thetas coordinates, partial theta and partials are lining up perfectly with our special vector fields 6 and the dollars. That's amazing.
It's like we finally found the right map to navigate this torus.
And since we know JGXY and JGY manix xetl, that translates to JGR theta and Dunbaf wafaleta and JVex. This looks exactly like how the complex structure acts on the real and imaginary parts of Celicoil Quas is Duller. It's like a perfect match.
We've basically found those local coordinates where the almost complex structure JG by acts just like the complex structure on math.DG. It's a big win.
Huge win. So this brings us to proposition 1, which states the map d theta is a holomorphic universal covering map. Deep breath. From the complex plane mass BBC with xi, the theta plus 2a, to our standard torus TR with its complex structure.
Lots of big words there.
I know. Let's break it down. What's a holomorphic universal covering map?
Okay, first, covering map. Imagine you're unwrapping the torus, laying it out flat on the complex plane. That's kind of what a covering map does. It's a map from one space to another, in our case, from math BBC to the torus, such that every point on the torus has a neighborhood that's evenly covered by the map.
Okay, like peeling an orange and laying out the peel flat.
Sort of. Each piece of the peel, that's like a neighborhood, and it comes from a specific region on the orange. And in our case, those regions on the complex plane, they're mapped in a nice continuous way onto the torus without any tearing or folding.
Okay, I see the covering part. What about universal?
Universal means that the complex plane, it's simply connected, no holes.
Yeah.
And any other covering space of the torus, any other way to unwrap it, can be gotten from math BBC by another covering map. It's like the most fundamental way to unwrap the torus.
And holomorphic.
Holomorphic means that the map PIC, PI, it preserves the complex structure. It's a fancy way of saying that PI maps complex directions in math PVC to complex directions on the torus in a way that's consistent with how the complex structure works.
So it's not just any old unwrapping. It's a complex structure preserving unwrapping.
Exactly.
The paper then sketches out the proof, mentioning that feed, the way we parameterize the torus in math Beatties, is already a covering map. And feed S theta F1S, that's just changing coordinates smoothly. So their composition, pi sec v psi, it inherits those nice properties. But the key is to check that holomorphic condition.
Right. To show that, the paper uses a local frame on the torus given by Zandi dollar partial theta, and Z dollar is V partial feet. This feet, it's just a way of pushing forward our vector fields from the parameter space to the actual surface. We know how JT acts on these. Right. Fractal R plus R code R plus Z dal or Z tau R plus Z dollar are 1.
Okay, so that's the complex structure on the torus, how it acts on those special directions.
And we also need to see how the differential of theta, that's dti, acts on the basis vectors partial theta and partials in math. Remember e pi theta f1s, which is just d p data, and partial theta festa, so partial theta, and partial theta, z pi phi, z t phi, and d pi 1 Garćıa theta pi. Then d pi t 4r plus r theta, z pi r p tar plus r cos partials, z pi p plus r z 22. And by carefully applying the complex structures, we can check that the holomorphic condition holds. It's a bit technical, but the takeaway is that T-pi is a well-behaved map that respects the complex structures.
So we've successfully unwrapped the torus onto the complex plane, but we have to remember torus are periodic, right? They loop around.
Absolutely. That's crucial for understanding the global structure.
The paper then defines this ET, or the ratio of the big radius to the small radius.
It's like a measure of how fat the donut is.
Exactly. And then it introduces this integral dx 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 must frac swart plus poi gx dxt. That's a lot to unpack. What's the significance of this omega?
This omega pops up because of the periodicity of our function phi. Remember how c phi is connected to t phi, which is an angle? Well, if you add 2 phi to phi, you're basically going a full circle. And because of the way phi is defined, phi plus maybe a, where ds is any integer.
So every time we go around the circle, $5 increases by a mega. It's like a built-in step size. Can we go through why that periodicity holds for $5?
Sure. So f phi in phi far plus r cos a. If we look at f phi plus 2 millipi, it's in phi r plus r co y. It's in phi plus 2 millipi. We can break this integral into mere pieces, each covering a full period of 2 millipi plus a leftover bit. F phi plus r co r plus r cos a plus r cos r plus r cos a plus r cohac plus r cos x plus r co I plus r cos I. Now, in each of those 2 millimit cos, we can shift our variable, like, let's say, on time 2k1 pi in the Calth integral. This shifts the integration limits to be from 0 to 2 mil. And because coas is periodic cos I, each of those integrals becomes in phi r plus r co, which is just the mega of those. The last bit, in phi plus 2 pi, we shift again using salpha phi r, and it becomes in phi, which is 3. Put it all together, and we get f phi plus 2 melody plus f phi.
So that shifting trick really brings out the periodicity of the OFL. Now, how does this connect to our covering map, pi theta F1?
Okay, so phi theta or torus parameterization, it's periodic with period 2L in both theta and phi. It's phi theta plus 2 and phi. Now let's look at pi theta plus 2 mil theta key wall plus new angle. Now there's phi theta plus 2 mil plus no mega, phi theta phi and phi theta plus no mega is the same as phi theta phi. Using the periodicity of the mils, this is just phi theta plus 2 and phi, which is a phi theta plus 2 and phi. Putting it all back into pi LO, we get phi theta plus 2 mil plus 2 mil phi theta plus 2 mil phi theta phi. Phi theta theta. So people is periodic too, with periods 2 into theta and to mega.
So it's like a grid of repeating units in the complex plane.
Exactly. And this periodicity allows us to define a new map at Lawler from this quotient space PBC to the torus P by dz by pi theta plus I by dzc.
Okay, we're hitting a lot of concepts here. What's this quotient space all about?
So the notation $2 math.DG, it's describing a lattice in the complex plane. It's all those points you get by adding multiples of $2 in the real direction and multiples of I omega in the imaginary direction. The quotient space, math BZ plus I omega, it's what you get by taking the complex plane and basically gluing together any 2 points that are related by this lattice.
Like folding it up?
Yeah, kind of. You're identifying those points, making them the same, and that creates a torus. It's like we took that flat plane and rolled it up in both directions.
Amazing. And because our pile is so well behaved, respecting the complex structure and the periodicity, this map dollar, it becomes a biholomorphic map.
Ever look at a donut and think, maybe there's more to this than meets the eye?
More than just a delicious treat.
Exactly. Today, we're going beyond breakfast and diving deep, way deep into the fascinating world of these shapes, which mathematicians call tori.
Tori, yes. Plural of torus.
Right. And what's really cool is that tori that look totally different can actually be, like, mathematically the same from a certain point of view.
It's like discovering that a basketball and a football, even though they seem different, are both fundamentally spheres.
That's a great analogy. This concept is called conformal equivalence. It's our key to unlocking some surprising connections.
We all have an intuitive idea of a torus, that classic donut shape.
Right, the kind with a hole in the middle.
But math lets us be much more flexible in how we define and construct these surfaces. And what's truly mind-blowing is when these different constructions, which might look nothing alike geometrically, turn out to share a common, complex structure.
So like a hidden blueprint they both follow.
Exactly. This shared structure is at the heart of conformal equivalence. It tells us that these surfaces are, in a very real mathematical sense, the same.
This is already getting my brain in a twist. Our guide for this journey is a paper called Hopf tori and Standard tori.
A classic.
I was amazed by how this paper explores these deep ideas using tools from differential geometry that are, well, relatively accessible. Usually you need some heavy-duty math to tackle these concepts.
It's a testament to the elegance of the approach.
Our mission in this deep dive is to untangle the conformal relationships between 3 main types of tori. The standard torus, that's the classic donut.
One we all know and love.
Yep. Then we have the product torus, the more abstract mathematical construction. And finally, a rather mysterious object called the Hopf torus.
A real head-scratcher.
We're going to see how these seemingly disparate mathematical entities are actually deeply intertwined.
And trust me, it's not just about satisfying mathematical curiosity, though that's definitely a big part of it. These ideas have implications in broader fields. Think Riemann surface theory, which studies the geometry of surfaces in the complex plane. That relies heavily on understanding how tories are classified.
Wow, so it's connected to complex analysis too.
Absolutely, and maybe even more surprising, these concepts have links to theoretical physics, particularly in areas like string theory.
Whoa, that's pretty far out.
And even to the study of surfaces embedded in three-dimensional space, like Willmore surfaces, which deal with minimizing bending energy. So what might seem like a niche area of math is actually at the crossroads of many important research fields.
Okay, so the stakes are high. Let's start by introducing the players. First up, the standard torus, often denoted as T or $. Picture this. You have a circle with a small radius. We'll call it torus.
Got it.
Now, rotate that circle around a line, but here's the twist. That line isn't passing through the center of the circle, it's a distance away, where $1 is bigger than tor away.
Ah, so it's like swinging a hula hoop around your body, not through your hand.
Precisely. That swirling motion creates our classic donut. Now, since this torus lives in 3D space, which has its own way of measuring distance, the Euclidean metric, the surface of the torus inherits a way to measure distances too. We call this the induced Riemannian metric.
It's like the torus inherits its ruler from the 3D world it lives in.
Makes sense. And the paper gives us a formula for this induced metric, denoted by $. It's written as r plus r d theta 2 plus r2 d theta 2.
Now that might look intimidating, but let's break it down.
Okay, so we have d theta and tt. What are those?
There are angle coordinates. Imagine you're an ant crawling on the torus.
I love this ant analogy.
The theta tells you how far you've gone around the hole of the donut the long way around, and the theta tells you where you are on the smaller circular cross-section of the donut.
Like, am I on the outer edge or the inner curve?
Exactly.
Okay, got it. Now, what about the d theta 2 and the d2
These represent teeny tiny changes in those angles. Imagine taking the smallest step you can in either direction. The theta 2 and the theta 2 are related to the square of the distance you travel with those tiny steps.
Okay, so they're measuring infinitesimal changes.
Right. And the coefficients in front, theta plus r cos phi for theta up to 2 and 2 to par for theta up to 2, these are crucial. They tell us how those tiny changes in angles translate into actual distances on the curved surface of the torus.
So they're like scaling factors.
Exactly. For instance, for theta plus 2 theta in front of the theta 2 tells you that the distance you cover when you change theta a tiny bit depends on where you are on the smaller circle, determined by quanta. It makes sense because the circumference around the hole is bigger on the outside of the donut than on the inside.
I see. So the metric dollar combines these two ways of moving around the hole and around the cross-section and tells us the infinitesimal distance squared.
Precisely. And remember, this is all about understanding how distances are measured on this curved surface.
Now, the paper introduces a new concept, the almost complex structure, denoted as $s. It's supposed to be compatible with our metric $s and the orientation of the torus.
Ah, yes, the almost complex structure. Think of it as a rule that tells you how to consistently define a 90-degree rotation at every point on the surface.
Like turning a quarter of a turn.
Exactly. But on a curved surface like a torus, it's more subtle than on a flat plane. This rule, $, needs to play nicely with the metric dollars. That means if you rotate two tangent vectors using $, the lengths and angle between them should be consistent with how the metric measures things.
Okay, it needs to respect the way we measure on the torus.
Precisely. It also needs to respect the orientation. Think of it like distinguishing between clockwise and counterclockwise on the surface.
So GeoGebra gives the torus a structure that locally looks like the complex plane.
Exactly. Remember how in the complex plane we have multiplication by the imaginary unit all dollars, which is like a 90-degree rotation?
Right, like multiplying by all $1 rotates a complex number in the plane.
GeoGebra is doing something similar on the torus, but in a way that's compatible with its curved geometry.
The paper shows how this GeoGebra acts on the coordinate vector fields partial theta and partial phi.
These vector fields just capture the directions of change as we vary our coordinates. Partial theta points along the long circular direction, and partial phi points along the circular cross-section.
Right. And the paper says JJ partial phi plus partial theta psi. And these equations tell us what happens when we take those basic directions and apply our 90-degree rotation, GeoGebra. The first one says that rotating partial theta gives us something proportional to partial phi, but the scaling factor depends on phi.
So the rotation isn't uniform.
Exactly. The scaling factor φr plus r cos tells us that the effect of the rotation depends on where you are on the cross-section of the torus.
It's like the strength of the rotation changes depending on your position. A good way to think about it. And the second equation tells us that rotating partial phi gives us something proportional to partial theta, again with a scaling factor that depends on mathematic.
So it rotates in the opposite direction and also has a variable strength. What's the significance of this non-uniformity?
It suggests that our initial coordinates, theta and vela, while good for describing the geometry, aren't the ideal coordinates for capturing the complex structure. In a true complex coordinate system, we'd want the action of our 90-degree rotation to be much simpler.
More like just multiplying by $a in the complex plane.
Precisely.
So the hunt is on for better coordinates. The paper introduces two special vector fields, 6 partial phi and dollars plus partial phi. It claims they're crucial because they satisfy some cool properties.
These vector fields are our heroes.
The first property is xy. This involves the Lie bracket of $6 and dollars, a concept that sounds pretty intimidating.
The Lie bracket measures how much the flows generated by the vector fields fail to commute. Imagine you're at a point and you flow along 6 for a bit, then along dollars. Now do it the other way around. Flow along dollars and 6. If the Lie bracket is 0, it means you end up at the same point, at least infinitesimally. The order doesn't matter.
So 6 and dollars are commuting vector fields.
Precisely. Their flows play nicely together.
The other two properties are jgxy and jgy equals all in these is x. Now, these really do look like complex numbers.
Right. It's like the vector field $6 is our real direction, and rotating it by jg gives us our imaginary direction. Rotating it again gives us a dockle, like multiplying by twi equals nages of 1. This is a strong hint that 6 and dollar form a natural basis for a complex structure.
Like they're setting the stage for complex coordinates.
Exactly. And this is where Frobenius's theorem comes in. This theorem guarantees that because our vector fields 6 and other commute, we can find local coordinates, let's call them AV, where partial is the same as 6 and partial AV is the same as the dollar.
So these Guido ordinates align perfectly with our special vector fields.
Exactly. And in these coordinates, the action of judo way becomes G partial U, partial phi L5, and Gdo G partial phi.
Which looks just like how multiplication by all dollar works on complex coordinates.
It's beautiful, isn't it? We found a local perspective where the torus acts just like the complex plane.
Amazing. Now, to actually find those G-double coordinates, the paper introduces a function f Yido phi r plus rgox. It points out that since FRD duo C, the derivative of dval, denoted d dou phi, is always positive. Why is that important?
That's a great question. Because the derivative is positive, it means that $5 is strictly increasing. And that means it has a well-defined inverse function, which we'll call phi dollar. This inverse function will be our key to transforming the phi coordinate into the imaginary part of our complex coordinate.
So $5 is helping us bridge the gap between our angle coordinate deal and the complex world.
Precisely. It's a crucial intermediary.
The paper then looks at what happens when we follow the flow of the vector field, Pfaffer R plus Was-Harkofi. It says if we start at a point, say it flow along for a time too, the theta coordinate stays put at theta $2, but phase or t changes to pst. Now, theta satisfies a certain differential equation, but the clever part is that if we consider for t, its derivative is simply 1. How does that work?
It all boils down to the chain rule. The derivative of respect to tall is full of 4 times 2, and that xrt is given by the differential equation. When you plug those in, magic happens. Some terms cancel out beautifully, and we're left with just 1.
It's always satisfying when things simplify so elegantly. So if the derivative is 1, that means t-phi is just some constant.
Right. And using the initial condition that phase r, we can figure out that the constant is phi, so we have phi4 plus a fesh.
And from there, we can use the inverse function phi of 1 to find the little phi explicitly.
Exactly. We get Basset f1t plus fd. This tells us exactly how the fact coordinate changes as we move along the flow of Dasset.
Okay, so we've tamed the flow of dollars using our clever function dollars. Now, the paper defines a maplet, let's say, and proposes that zeta, theta plus, provides the analytic coordinates we've been searching for.
This is it. The moment of truth.
It checks by looking at the partial derivatives of Basset. The derivative with respect to the theta is just $1, which matches our $6. That seems pretty straightforward.
It is. The derivative with respect to dollars is a bit more involved, but using the inverse function theorem and the definition of dollars, we can show that it matches our dollars.
So our new coordinates perfectly align with our vector fields 6 and dollars.
Which means that test AG acts on them just like multiplication by $1 acts on the real and imaginary parts of a complex number.
It's beautiful how everything falls into place. We finally found our complex coordinates. This leads to proposition 1, which says that the map fun, is a holomorphic universal covering map from the complex plane to our standard torus, fun.
This proposition is telling us that we can unwrap the complex structure of the torus onto the complex plane in a way that preserves all the essential information.
Okay, so it's like we're laying out a flat map of our curved torus, but in a way that respects the complex structure.
A perfect analogy.
What do holomorphic and universal covering map mean in this context?
Holomorphic means that the map respects the complex structure, meaning it preserves the notion of 90-degree rotations and all the nice properties that come with it. A covering map is a way of mapping one space onto another so that locally it looks like just laying one sheet on top of another.
I see. And universal?
Universal means that our complex plane is, in a sense, the biggest space that can cover the torus in this way. Any other covering space can be obtained from the complex plane.
So it's the most fundamental covering space.
Exactly. And the proof of this proposition involves checking that our map satisfies all the required properties. It's a bit technical, but the key is to show that the differential of PAP intertwines the complex structure tensors correctly.
So it's all about making sure the rotations behave consistently between the complex plane and the torus.
Precisely.
Okay, so we've successfully mapped our torus onto the complex plane. But to understand the global structure, we need to account for periodicity.
Right, the fact that going around the torus brings you back to where you started.
The paper defines IRR, the ratio of the big radius to the small radius. This intuitively captures the shape of the donut.
Like how fat or thin it is.
It also introduces a quantity omega r plus RSA, which turns out to be equal to frac r xz, which turns out to be equal to frac r c. This omega r comes from the periodic behavior of our function, frac hour.
Remember how we used $5 to relate our angle coordinate to the imaginary part of our complex coordinate?
Right. So what does this omega have to do with periodicity?
It captures the fact that phi is periodic, meaning that if you shift theta by a multiple of $2, the value of phi changes by a multiple of tomega.
So domegi is the period of tele in a sense.
Exactly. And this periodicity of phi's carries over to our covering map phi. The paper shows that p theta plus 2 pi m s plus net omega, where $9 are any integers.
So shifting our complex coordinate by multiples of 2 pi's in the real direction and multiples of tomega in the imaginary direction doesn't change where we land on the torus.
It's like walking around the torus and ending up back where you started.
That periodicity lets us define a map from the quotient space plus I omega stay to our torus daylies.
This quotient space is just the complex plane where we identify points that differ by those periods.
So it's like we're gluing together points that correspond to the same location on the torus.
Precisely. And this gluing process creates a new space that has the topology of a torus, but now it also inherits a complex structure from the complex plane.
And the map dollars captures this complex structure.
Yes, Della turns out to be a biholomorphic map.
Which means?
It means it's a one-to-one onto map that preserves the complex structure and has an inverse that also preserves the complex structure. Basically, it tells us that the quotient space and the torus are essentially the same from the perspective of complex analysis.
They have the same complex shape, so to speak.
Exactly.
This brings us to Theorem 1, which states that the standard torus Gilera-Fear is biholomorphic to the complex torus math plus Delametti A. This theorem is the culmination of all our efforts. It tells us that the standard torus, our familiar donut, is fundamentally the same as a specific quotient of the complex plane, at least when it comes to complex structure.
It's like we found the complex DNA of the donut, and corollary 1 follows directly. If two standard tories have the same ratio 2 aisles, they're conformally equivalent.
Which makes intuitive sense. That ratio determines the overall fatness of the donut. If the ratio is the same, they have the same underlying complex shape, even if their actual sizes are different.
Precisely.
Now, things are about to get even more abstract. The paper talks about the range of the function theta1, where RR dual. What values can this function take?
As it varies from slightly above 1 to infinity, omega dual goes from infinity down to 0. This means that for any positive real number, there's a standard torus with a corresponding omega dual. And that means we can represent any standard torus as a complex torus lambda tau with a lattice lambda tau plus IY Mach or use a positive real number.
Okay, and this leads to the moduli space of elliptic curves, denoted by $.
Ah, the moduli space. It's like a map that shows us all possible conformal equivalence classes of elliptic curves. Remember, elliptic curves are just complex torus of genus 1.
So it's a way of organizing all possible complex structures on a torus.
Exactly. And our period ratio tau acts like a coordinate in this moduli space. However, there's a subtlety. Different values of tau can actually correspond to the same conformal class. That's because of the action of the group C-cell 4 terms.
C-cells?
Cis2 afterns. It's a group of 2 by 2 matrices with integer entries and determinant 1. These matrices can act on our period ratio tau through a special kind of transformation called a linear fractional transformation.
So even though we have all these different tau values, some of them are essentially the same because they're related by this group action.
Precisely. And that leads to the idea of a fundamental domain, which is a region in the upper half plane where each point represents a unique conformal class.
It's like choosing one representative from each group of equivalent tau values.
A good way to think about it. And the paper gives an example of this equivalence using the Mobius transformation tau maps to O1 tau.
That's the one associated with the matrix begin matrix 701 and math.DG levels.
Right. And it leads to proposition 2, which says that if $1 squirt 2, then our standard torus is conformally equivalent to another standard torus with different radii, but related through this transformation.
So even though those tories have different radii, their complex structures are fundamentally the same because their period ratios are related by this Sinelo-2 Sailor math.BZ.
It's a reminder that conformal equivalence goes deeper than just the surface appearance.
Okay, we've explored the standard torus in depth. Let's introduce our second type of torus, the product torus.
Another fascinating character in our story.
For $0 lekalita 1, the paper defines the product torusor as the surface several dollar times S01 with a metric dollar equals d theta 2 plus a d phi 2 2. Now $7 is just the unit circle in the complex plane.
So $7 times S1 is like taking two circles and combining them in all possible ways. You get a torus shape.
Right. And the metric dollar tells us how to measure distances on this product torus. The data controls the relative size of the second circle compared to the first.
It's like stretching or shrinking one of the circles.
The paper mentions that any product torus with a metric of the form BD theta 2 plus CD 32 is conformally equivalent to some C theta 2. Why is that?
It's all about scaling. Remember, conformal equivalence doesn't care about distances, just angles. So we can always rescale our coordinates to get rid of the bolus and the two vectors and be left with something proportional to del theta 2 plus d phi 2 2, which is essentially the metric of C adu after a potential relabeling of a theta and ball.
So by cleverly choosing our coordinates, we can always make any product torus look like one of our C dories.
Exactly. It's like putting on a different pair of glasses to see the same underlying structure.
The paper then introduces two orthogonal vector fields, $6 partial theta and diagonal chorda and theta. It says they're orthonormal and commute, and their flows define analytic coordinates.
These vector fields are our friends. Orthonormal means they're perpendicular to each other and have unit length with respect to the metric dollars. And because they commute, their flows create a nice coordinate system where the metric looks like the standard Euclidean metric.
Like a local patch of flat space within our curved torus.
Precisely. And those coordinates turn out to be analytic coordinates, meaning they're compatible with the complex structure.
So we've found another way to view the product torus as a complex manifold.
And the paper describes a biholomorphic map $, that maps points in the complex plane, modulo a certain lattice, to points on our product torus 7.
This map, $, essentially glues the complex plane together in a way that creates a torus with the same complex structure as to dollars.
Right. And Theorem 2 generalizes this result, stating that any product torus with a metric of the form BD theta 2 plus ad phi theta 2 is conformally equivalent to a specific complex torus, whose lattice depends on the ratio $4.
Okay, so we have a good handle on product tori now. And corollary 2 connects them back to standard torus, stating that the standard torus 2 ladder is conformally equivalent to the product torus rows a half 2 or a half 2 or 2.
It's a beautiful bridge between those two seemingly different constructions.
Now for the most enigmatic player, the Hopf torus.
Hold on tight, things are about to get weird.
To understand Hopf tori, we need to venture into the world of quaternions, denoted by math.BBQ. These are like complex numbers on steroids. Instead of just one imaginary unit, they have three. I-glander and I-dal.
The whole family of imaginary units.
And they have some strange multiplication rules. But the key is that they allow us to describe rotations in 3D space very elegantly.
Quaternions are a powerful tool for understanding geometry in higher dimensions.
The paper describes the three-sphere 3s3 roles as the set of all unit quaternions.
It's like the surface of a four-dimensional ball, which is mind-boggling to imagine.
And within the quaternions, we can identify the two-sphere 2s22 as the set of unit quaternions with no real part and no component along other ball.
So it's a specific slice of this four-dimensional sphere.
Now comes the Hopf fibration, a map by that takes a point on 3s23 dollars and maps it to a point on 2 shards. The definition given in the paper seems a bit off, so let's focus on the concept rather than the precise formula.
The Hopf fibration is a way of projecting down from the 3-sphere to the 2-sphere. Imagine fibers, like threads, connecting points on 3s33 to points on 2s2 times.
Okay, so it's like a special kind of map that preserves this fiber structure.
Exactly.
Now, a Hopf torus paper is defined as the inverse image of a closed loop, or Jordan curve. TFA is $18 a tuber on their Hopf map.
So if you take all the fibers that lie above the points on that loop, they form a torus embedded in 23 layers.
It's like taking a necklace and twisting it around to form a donut shape.
A very abstract necklace. And this Hopf torus inherits a metric from the 3-sphere, which gives it a complex structure.
So despite being embedded in this weird four-dimensional space, the Hopf torus still has a well-defined complex structure.
It's remarkable how these concepts carry over to higher dimensions.
The paper then introduces a connection in one form, a horizontal bundle, and a horizontal lift, all concepts from differential geometry that help us understand how to move on this chorus in a way that's compatible with the Hopf fibration.
Think of it as finding the right way to walk on the torus so that your shadow on the 2-sphere follows the loop that defines it.
And it turns out that this Hopf torus, even though it lives in a Resolute $3, can be unwrapped onto the complex plane just like the standard torus.
It's all about finding the right coordinates and understanding how the complex structure is encoded in the geometry of the Hopf fibration.
The paper describes a map that does this unwrapping, and it shows that the induced metric on the complex plane is conformal to the Euclidean metric, meaning that locally, the Hopf torus looks just like the complex plane.
It's another instance of this beautiful correspondence between complex analysis and the geometry of tor.
The paper then delves into some details about the geometry of the loop passed to do that defines the Hopf torus, introducing concepts like geodesic curvature and signed area.
These geometric properties of the loop turn out to be crucial for understanding the complex structure of the Hopf torus.
And this leads to Theorem 3, which states that the complex torus corresponding to the Hopf torus is determined by the length and signed area of the loop.
It's a beautiful connection between geometry and complex structure.
And remarkably, the paper shows that by considering all possible loops on 1,2A2, we can actually generate all possible complex structures on a torus.
This means that Hopf tori, even though they're constructed in this very specific way, are incredibly versatile. They can capture all the richness of the moduli space of elliptic curves.
It's like finding a hidden doorway that leads to the entire universe of complex tori.
A very poetic way to put it.
The final part of the paper connects Hopf tori back to standard and product tori, showing that there are conformal equivalences between all three types.
It's like closing the loop, so to speak.
The exact formulas for these equivalences seem to have some minor inconsistencies in our excerpt, but the overarching message is clear. These seemingly disparate constructions are all intimately related through the lens of complex structure.
It's a testament to the power of abstraction. By focusing on the essential properties, we uncover deep connections that might be hidden if we just look at the surface appearance.
This deep dive has been a real mind-bender, but it's also incredibly illuminating. It shows how different areas of mathematics can intersect in unexpected ways, and how abstract concepts can shed light on concrete geometric objects.
And it opens up a whole new way of thinking about tori, revealing hidden connections that might not be apparent at first glance.
It makes you wonder what other hidden connections might be lurking out there, just waiting to be discovered if we're willing to take a step back and look at things from a different perspective.
That's the beauty of mathematics. There's always more to explore, always deeper connections to uncover.
Thank you for joining us on this adventure into the world of tori and conformal equivalence. We hope it sparked some new ideas and inspired you to explore the hidden depths of mathematics.
And who knows what other fascinating discoveries await us.
Thanks for tuning in to this deep dive. We'll see you next time. All right, welcome everyone to another deep dive. Today we're looking at tori.
Tori, yes.
Specifically, we're going to be talking about the conformal equivalence of tori.
Right.
And complex dimension 1, so that means real dimension 2. And
The usual.
Yeah, the usual. The paper that we're looking at is called Hopf tori and Standard tori.
Okay.
By Leonardo A. Cano Garćıa. And
sounds like fun.
Yeah, it's a good one. So he starts out by saying, some of this stuff might be familiar to people if you're, really into complex analysis and Riemann surface theory and all that. But he wants to sort of lay out a clear perspective on product tori and standard flat tori.
I see.
And how they relate to Hopf tori, which is pretty cool. So
yeah, I'm intrigued.
Yeah. So the moduli space of tori is parameterized by the upper half plane the action of SL2Z.
Okay.
So, this is kind of a classic thing, right?
Big success.
You've got this this space of the different ways that you can define a complex structure on a torus. And our mission today is to try to understand.
I like it. A mission.
Yeah. Where do product tori and standard tori live in this space?
Okay, great.
And that's precisely what theorems 1 and 2 in the paper are all about.
Yeah.
So
sounds good.
As a byproduct of all of this, we're going to understand how these tories can be realized as Hopf tori.
Hopf tori, yeah.
So these are related to closed curves on the two-sphere.
Okay.
And a really cool result is that standard tori and product tori are always conformally equivalent.
Always. Wow. Okay.
So
that sounds interesting. I'm looking forward to that.
Yeah. So he starts out with some definitions. So a torus in this context is just any manifold that's diffeomorphic to S1 cross S1, so just the product of two circles.
Right, the donut shape.
Yeah, donut shape, exactly. And then a complex torus is a torus equipped with a complex structure.
Of course.
So,
makes sense.
Standard tori, which he denotes T sub r, comma r. These are generated by rotating a circle of radius, little r, centered at big R, 0 in the XC plane. Okay. Around the y-axis.
So we're in 3 dimensions now.
Yeah, we're in 3 dimensions. You've got this circle and you spin it around, and that gives you a torus.
Okay.
And of course, big R has to be bigger than little r.
Right. Otherwise, it gets all tangled up.
Otherwise, it intersects itself. And the induced Riemannian metric from IR3 defines its complex structure.
Okay.
Product tori are these are complex tories associated with complex structures on S1 cross S1, which are induced by Riemannian metrics of the form G equals AD theta squared plus BD phi squared.
Okay.
In coordinates, theta A phi goes to E to the I theta, E to the I phi.
Right, standard coordinate.
Where A and B are real positive numbers.
Okay,
so
makes sense.
The motivation for all this comes from visualizing conformal classes of metrics on S1 cross S1 through embeddings into IR3. And the paper references Garcia's theorem, which says that every elliptic curve can be realized by an embedding of S1 cross S1.
Into IR3.
Into IR3.
Okay.
So, and Pinkel also did some work on this earlier. So
we have this like geometric picture of elliptic curves, which are complex stored.
Exactly. Yeah. And standard and product tori are just, natural families
to look at.
Right?
Okay.
So, let's see. Section 2, he starts out by looking at the conformal class of a standard torus.
Okay.
So, he defines this universal covering map of theta and theta. Right. And it's equal to, it's a vector.
Okay.
The first component is r plus little r cosine phi times cosine theta.
Okay.
The second component is r plus little r cosine phi times sine theta. And the third component is r sine phi.
Right. So I can kind of see how that gives you the torus, right? You've got the cosine theta, sine theta, that's rotating around the y-axis. Right. And then the r plus little r cosine phi, that's giving you the radius of the circle that's being rotated. And then the r sine phi is the height.
Exactly.
Okay, cool.
Yep. So then he pulls back the Euclidean metric on IR3 via this map, and he gets the induced Riemannian metric G on the torus. Okay. And it's r plus little r cosine phi squared d theta squared plus little r squared d phi squared.
Okay. And so those coordinates, the antiphi, those are orthogonal, right?
Yes, because the metric is diagonal.
Right. Okay.
And then you get an almost complex structure from that that's compatible with the metric G. Okay. Which he denotes J sub G. Yep. And it acts on the coordinate vector fields as J sub G of d by d theta is equal to r plus little r cosine phi over little r times d by d theta. And J sub G of d by d phi is equal to minus r over r plus little r cosine phi times d by d theta. And the point here is that
Yeah.
theta and phi themselves are not analytic coordinates.
Right, because that complex structure is it's kind of twisting things around. It's not just multiplying by I.
Exactly.
Okay.
So he then defines these two vector fields, x and y. So x is just d by d theta.
Okay.
And y is r plus little r cosine phi over r times d by d phi. And these satisfy some crucial properties. The Lie bracket of x and y is 0.
Okay.
J sub g of x is equal to y, and j sub g of y is equal to minus x.
Right. So what's the point of those properties? Like, why are those crucial?
So the fact that the Lie bracket is 0 means that locally you can find coordinates u and v.
Right.
Where d by du is equal to x and d by dv is equal to y.
Okay. I remember that from differential geometry. That's Frobenius's theorem.
That's right. That's
yeah,
right.
Yeah.
And then the other two properties tell you that in those coordinates, j sub g acts like multiplication by I.
Right, because it's sending d by du to d by dphi and d by dv to minus d by du.
Exactly. So u and v are essentially the real and imaginary parts of an analytic coordinate.
Right. Okay, so that's the goal then.
That's the goal.
Find those coordinates, u and v.
Yeah. So to do that, he defines this function f of phi, which is the integral from 0 to phi of r over r plus little r cosine x dx. And if you differentiate that, you get f prime of phi is equal to r over r plus little r cosine phi.
Right, just by the fundamental theorem of calculus.
Exactly. And this thing is always positive because r is bigger than little r.
Right, so the denominator is always positive.
Yeah. So f is a strictly increasing function of phi, which means it has a well-defined inverse, which he calls f inverse.
Okay.
So then he looks at the flow of the vector field, y, starting at a point theta naught, phi naught.
Okay.
And he calls this flow gamma sub theta naught, phi naught of t.
Okay. And
it's equal to theta naught, ci of t. So the theta component doesn't change because y only has a phi component.
Right.
And psi of t satisfies this differential equation. Psi chron of t is equal to r plus little r cosine of psi of t over r, with initial condition psi of 0 equals phi naught.
Right. So that's just saying that the tangent vector to the flow is equal to the vector field at that point.
Exactly.
Right.
Now, if you look at f of psi t, and you differentiate that with respect to t, you get, well, by the chain rule, it's f prime of psi of t times c psi prime of t.
Right.
And then if you plug in the formulas for those, you get 1.
Wow. Okay.
So that means f of psi of t is just equal to t plus a constant.
Right.
And if you plug in t equals 0, you get that the constant is equal to f of phi naught. Okay. So f of c of t is equal to t plus f of phi naught.
Right.
Which means psi I t is equal to f inverse of t plus f of phi naught.
Okay. So that gives you the flow explicitly.
Exactly.
All right.
Now he defines a new map, f of theta and s, which is equal to theta comma f inverse of s. And he claims that z equals theta plus is are analytic coordinates.
Okay. So how do we see that?
Well, we need to look at the partial derivatives of s with respect to theta and s.
Okay.
So the partial derivative of f with respect to theta is just 1, 0.
Okay.
Because f inverse of s doesn't depend on theta.
Right.
And if you push that forward by you get d by d theta, which is our vector field x.
Okay.
And then the partial derivative of with respect to s is 0, comma, d by ds of f inverse of s.
Okay.
And if you use the inverse function theorem, you can compute that.
Yeah.
And you get r plus little r cosine phi over r.
Okay.
And then if you push that forward by s, you get r plus little r cosine phi over r times d by d phi, which is our vector field y.
Okay.
So in the theta s coordinates, d by d theta corresponds to x and d by ds corresponds to y.
Right.
And we know that j sub g of x is y and j sub g of y is minus x.
Right.
So that means that in these coordinates, j sub g acts like multiplication by I.
Right, just like the standard complex structure.
Exactly.
Okay, that makes sense.
So this leads to proposition 1, which says that the map a of theta s, which is defined as a of theta sp, is a holomorphic universal covering map from the complex plane to the torus.
Okay, and holomorphic means?
Holomorphic means that it's differential.
Right.
Commutes with the complex structures. So dA composed with j sub c is equal to j sub t composed with d.
Or J sub C is the complex structure on the complex plane.
Exactly. And J sub T is the complex structure on the torus.
Okay.
So you can check this by computing the differentials of A and how they act on the basis vectors.
Right.
And you get equations 5 and 6 in the paper.
Okay.
And then you just plug those in and check that the equation holds.
Okay. Sounds good.
Okay. So then he defines this parameter, A, which is equal to big R over little r,
Right.
and omega of A, which is the integral from 0 to 2 pi r over r plus little r cosine x dx. And this is equal to 2 pi over the square root of a squared minus 1, which is also equal to 2 pi times the square root of r over r squared minus 1.
Okay.
And this omega of a phi is going to be a period for our complex torus.
Okay, a period. So we're going to be quotienting by something involving omega.
Exactly. Exactly.
Okay.
Now, the function f of phi has this property that f of phi plus 2m pi is equal to f of phi plus m omega.
Okay, where m is an integer.
Yeah.
Right. And that just comes from the fact that the integrand is periodic.
Exactly.
Okay.
And this leads to the periodicity of the map.
Okay.
So if you shift theta and s by 2 pi m and omega,
Yeah.
you get the same point on the torus.
Okay. So that gives us a lattice.
Exactly. Exactly.
Yeah.
So you can define a quotient space of the complex plane by this lattice, which is 2 pi z plus I omega z.
Okay.
And then you get a map H from this quotient space to the torus,
Okay.
which is just defined by H of the equivalence class of theta plus IS is equal to A of theta.
Okay.
And this map is biholomorphic.
Right.
So that means that the standard torus is biholomorphic to the complex torus C modulo, this lattice.
Right, which is C modulo 2 pi z plus I omega of r over rz.
That's right.
Okay, and that's theorem 1?
And theorem 1, yeah.
Great.
And then corollary 1 says that if you have two standard tories with the same ratio of radii,
Yeah.
then they're conformally equivalent.
Right, that makes sense.
Yeah. And the range of omega of a deo is the whole positive real line.
Okay.
So that means that standard tories are biholomorphic to elliptic curves
Okay.
with period ratios tau equals iy, where y is positive.
Okay.
So that's the positive imaginary axis in the upper half plane.
Right.
But we have to remember that the moduli space of elliptic curves is not the upper half plane itself.
Right, it's the upper half plane modulo SL2Z.
Exactly. So there are different points in the upper half plane that correspond to the same conformal class.
Right, because you can have different lattices that give you the same torus.
Exactly.
Further.
And one important example is the Mobius transformation tau goes to -1 over tau, which
Okay.
corresponds to the matrix 0, -1, 1, 0 in SL2Z.
Right.
So this tells us that C modulo Z plus tau Z is conformally equivalent to C modulo Z -1 over tau Z.
Mm-hmm. Okay, so even if the period ratios look different, they might actually be the same.
Exactly.
Okay.
And then proposition 2 says that if 1 is less than R over R is less than the square root of 2,
Okay.
then the standard torus T sub RR is conformally equivalent to the torus T sub R prime. R prime, where R prime is the square root of R squared minus little r squared, and R prime is equal to R.
Okay.
And there's a projection between tori with 1 less than R over R less than the square root of 2, and tori with R prime over R prime bigger than the square root of 2.
Okay, so that's kind of interesting. It's relating tori with different ratios of radii.
Yeah. So to prove this, he defines a new ratio B.
Okay.
Such that the period ratios tau sub A and tau sub B are related by tau sub B equals -1 over tau sub A. And if you work out the details, you find that B is equal to A over the square root of a squared -1.
Okay.
And this function A over the square root of a squared -1, it's a strictly decreasing function on the interval 1 to the square root of 2.
Yeah.
And it maps that interval to the interval square root of 2 to infinity.
Okay. So that's where the projection comes from.
Exactly.
Okay.
Okay. Now, section 3 is about product tori.
Okay.
So for 0 less than or equal to 1, he defines S sub A to be S1 cross S1.
Okay.
With the metric G sub A equals d theta squared plus a d phi squared.
Okay.
And any product torus with a metric of the form b d theta squared plus c d phi squared is conformally equivalent to some S sub A.
Right, you just rescale the coordinates.
Exactly.
Okay.
So he defines these vector fields, x equals d by d theta and y equals 1 over the square root of a times d by d phi.
Okay.
And these are orthogonal, and they have Lie bracket 0.
Okay.
And their norms are both equal to 1. So they define local analytic coordinates.
Right, because of Frobenius.
Yeah.
Okay.
And the map G from C modulo Z plus I square root of Z to S1 cross S1,
Okay.
which is defined by G of the equivalence class of theta plus IS, is equal to e to the I theta, e to the IS over square root of A, is a holomorphism.
Okay, so that gives you the complex structure of the product torus.
Exactly.
Okay.
And theorem 2 says that if A is bigger than B is bigger than 0,
Okay.
then the product torus S sub A, B.
Which has metric BD theta squared plus AD phi squared.
Right. Is conformally equivalent to C modulo Z plus I square root of A over BZ.
Okay, and that's just rescaling again.
Exactly.
Okay.
And corollary 2 says that the standard torus T sub R is conformally equivalent to the product torus SA, where A is equal to the square root of R over R squared minus 1.
Okay, so now we've got this connection between standard tori and product tori.
Exactly.
Okay.
Now, section 4 is about Hopf tori.
Okay.
So first he reviews some stuff about quaternions. So the quaternions are this four-dimensional algebra over the real numbers.
Yeah, you've got one I, j, and k,
Right.
and I squared, j squared, k squared are all minus 1.
That's right.
And then you have I times j equals k, j times k equals I, and k times I equals j.
Right. And S3 is the set of unit quaternions, which is a 3-sphere.
Right.
And you can identify S2 with the unit quaternions that lie in the span of I, j, and k.
Okay.
And the Hopf vibration is a map from S3 to S2,
Yeah.
which is defined by pi of q equals q tilde times q, where q tilde is the conjugate of q.
Okay.
And there's an S1 action on the fibers.
Right, you can multiply by a unit complex number.
Exactly.
Okay.
Now, a Hopf torus is the inverse image under pi of a closed curve on S2.
Okay, so you take a loop on the sphere and you look at all the points in S3 that map to that loop.
Right.
Okay.
And it inherits a complex structure from S3.
Right.
Now, there's this connection, one form alpha on S3.
Okay.
And the horizontal bundle is the orthogonal complement of the vertical bundle, which is the kernel of pi. And if you take an alpha horizontal lift eta of a Jordan curve P on S2,
Okay.
parameterized by arc length, then the map chi of t plus I phi equals e to the I phi times eta of t is a universal covering map of the Hopf torus.
Okay.
And this map is holomorphic.
All right.
Now, there exists a function, u from the interval to the span of j and k,
Okay.
with norm 1, such that eta prime is equal to u times eta.
Okay.
And the tangent vector to p is given by p prime equals 2 eta tilde times u times I times eta.
Okay.
And the length of eta is half the length of p.
Okay.
Now, since eta of L over 2 and eta of 0 lie in the same fiber,
Yeah.
eta of L over 2 is equal to e to the I delta times eta of 0 for some delta.
Okay.
And delta is equal to A of P over 2, where A of P is the signed area enclosed by P.
Okay.
And this area is related to the geodesic curvature of P by the Gauss-Bonnet theorem.
Right.
So A of P is equal to 2 pi minus the integral of the geodesic curvature along P.
Oh.
Now, theorem 3 says that the complex torus T sub P associated to P is biholomorphic to C modulo 2 pi Z plus A of P over 2 plus IL of P over 2.
Okay. So that relates the complex structure to the geometry of the curve.
Exactly.
Right.
And then there's the isoperimetric inequality on S2, which says that A of P over 2 minus pi squared plus L of P over 2 squared is greater than or equal to pi squared.
Okay.
And this region, along with its reflection, covers a fundamental domain of SL2Z.
Okay.
So that means that Hopf tori exhausts all conformal classes
Wow. Okay.
of genus 1 Riemann surfaces.
That's pretty cool. So every complex torus is a Hopf torus.
Exactly.
All right.
And then theorem 4 says that every compact Riemann surface of genus 1 is conformally equivalent to S1 cross S1 with a metric pulled back from IR3 by some embedding.
Okay.
And this embedding can be chosen to be algebraic.
All right.
Okay.
Yeah.
Now, section 4.1 is about Hopf tori and product tori. So for 0 less than or equal to 1/2, he defines H sub t to be S1 cross S1 with the metric G sub t equals t squared, d theta squared plus 1 minus t squared, d phi squared.
Okay.
And any flat product torus is conformally equivalent to some H sub t.
Right. Just by rescaling. Yeah.
Exactly.
Okay.
Now you can embed this torus into the quaternions
Okay.
using the map of e to the I theta, e to the I phi equals t cosine theta plus t sine theta I plus square root of 1 minus t squared cosine phi j plus square root of 1 minus t squared sine phi k.
Okay. So that's a pretty explicit formula.
Yeah.
Right.
And this torus is invariant under the diagonal S1 action.
Okay.
And if you project it down to S2 using the Hopf vibration, you get a circle,
Okay.
which is parameterized by S goes to 2t squared minus 1 plus 2t square root of 1 minus t squared times cosine sj plus sine sk.
Okay.
So the Hopf torus S sub t is the Hopf torus associated to this circle.
Right.
And the area of this circle is 4 pi squared, and the length is 4 pi square root of 1 minus t squared. So by theorem 3, S sub t is biholomorphic to C modulo z plus t squared plus it square root of 1 minus t squared z.
Okay.
And if you apply the Mobius transformation, tau goes to minus 1 over tau.
Yeah.
And then add 1, you get I square root of 1 minus t squared over t.
Okay.
And this is the period ratio for the product torus S sub e, where A is equal to 1 minus t squared over t squared.
Okay, so that's proposition 3, right?
That's right. So conformal classes of flat product tori coincide with those of Hopf tori associated to circles.
Oh.
Okay. And finally, section 4.2 is about Hopf tori and standard tori.
Okay.
So if you have a standard torus with r over r bigger than the square root of 2,
Yeah.
let b equal the square root of r over r squared minus 1.
Okay.
Then by corollary 2, t sub rr is conformally equivalent to s sub b.
Right.
And by proposition 3, S sub b is conformally equivalent to h sub t of b,
Yeah.
where t is equal to 1 over the square root of b squared plus 1, which is equal to r over r. So that means that t sub r, rr, is conformally equivalent to the Hopf torus h sub t, where t is equal to r over r.
All right. And that's corollary 3.
That's corollary 3, yeah.
Right.
So that's the whole paper.
Wow. That was quite a journey.
Yeah.
So we've seen how these 3 families of tori,
Right.
standard tori, product tori, and Hopf tori, are all related. And they all live in this moduli space
Right.
of genus 1 Riemann surfaces.
Exactly.
And we've got these explicit formulas relating their parameters.
Wow.
So it's really quite beautiful how it all fits together.
Yeah, it is.
I'm curious, we've been looking at this from a very differential geometric point of view.
Right.
With all these metrics and embeddings.
Yeah.
But there's also this algebraic geometric side to the story,
Right.
With elliptic curves and modular forms and all that.
Right.
So I wonder if these insights about Hopf tori could shed some light on that side of things.
Yeah.
Maybe there's some connection there that we haven't explored yet.
Yeah, it's definitely something to think about.
Definitely.
Yeah. All right, well, that was a great deep dive.
Yeah, it was.
Thanks for joining me.
Thanks for having me.